Hello, everyone. Welcome to our presentation on basic algebra. Today, we'll explore the fascinating world of algebra, which is all about understanding mathematical symbols and how to work with them. In this session, we'll cover the fundamentals, including key concepts and rules. So, let's get started and discover the basics of algebra together. Let's take a closer look at this fascinating formula. A 2 minus b2 equals the product of a minus b and a plus b. This is known as the difference of squares, a very useful algebraic identity. The key idea here is that when you have two perfect squares separated by a subtraction sign, you can factor them into this product of two binomials. Notice how the terms inside the parentheses are a minus b and a plus b. These are called conjugates. This formula not only simplifies many algebraic expressions, but also helps us understand how certain patterns emerge in mathematics. Throughout this presentation, you'll see how such identities connect to broader concepts, making complex problems more manageable. So, mastering this difference of squares will be a powerful tool in your mathematical toolkit. Let's take a closer look at Formula 2, which is x plus a, x plus b, equals x squared plus the sum of a and b times x, plus the product of a and. What this formula really shows us is how to expand the product of two binomials. The key points here are the three parts. First, we multiply the two x terms to get x squared. Then, we add the coefficients a and b, multiply them by x, which gives us the middle term. And finally, we multiply a and b together to get the constant term at the end. This formula is fundamental because it connects to how we handle quadratic expressions and helps us understand the structure of binomials. It's all about breaking down complex expressions into manageable parts, which ties back to our overall theme of simplifying algebraic expressions. All right, let's take a closer look at Formula 3. This is the expanded form of the square of a binomial, specifically x plus y, 2. What this formula tells us is that when we square a sum, it's not just about squaring each term individually. Instead, we have to account for the interaction between x and y, so the formula states that x plus y 2 equals x2 plus 2xy plus y2. The key here is understanding the middle term, 2xy, which represents twice the product of x, and why this term arises from the fact that when you expand the binomial, you get two identical cross products, x times y and y times x, which are the same. That's why we combine them into 2xy. This formula is fundamental because it helps us quickly expand and simplify expressions involving squared binomials, and it connects directly to our overall theme of understanding algebraic identities. It shows how the parts of the sum interact when squared, giving us a clear pattern to recognize and apply in various problems. Let's take a closer look at Formula 4, which is x y2 equals x2 minus 2xy plus y2. This formula is all about expanding the square of a binomial. When we see x, y2, it means we're multiplying xy by itself, so we can think of it as xy times xy. Now, to expand this, we use the distributive property, often called FOIL in algebra. First, we multiply the first terms, x times x, which gives us x2. Then the outer terms, x times y, which results in xy. Next, the inner terms, y times x, giving us xy again. And finally, the last terms, y times y, which becomes plus y2 because a negative times a negative is positive. When we combine everything, the middle terms, xy and xy, add up to minus 2xy. So putting it all together, we get x2 minus 2xy plus y2. This formula is really useful because it allows us to quickly expand binomials squared without doing all the multiplication step by step. It also highlights the importance of understanding how binomials expand, which connects to broader concepts of algebra and quadratic expressions. In essence, this formula gives us a straightforward way to simplify and work with squared binomials, making our calculations more efficient and helping us see the structure behind these algebraic expressions.